Tonight, we're going to talk about the most disturbing exoplanets we've ever discovered. Astronomers have now confirmed more than 6,300 worlds orbiting other stars, and a striking number of them defy almost everything we once assumed a planet had to be. Worlds where the rain isn't water, it's molten metal or liquid glass. Worlds locked into orbit so tight that one side burns while the other freezes in permanent darkness. Worlds being slowly torn apart by their own stars. And worlds with no star at all, drifting through absolute cold and absolute dark. One of them is so massive that astronomers still can't agree on whether to call it a planet or something else entirely. By the end of tonight, you're going to understand exactly what's happening on each of these worlds and why so much of what we thought we knew about planets turns out to be wrong. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. For most of human history, we had no idea whether other stars had planets at all. The question wasn't scientific in any observational sense. It was philosophical. Stars were points of light, impossibly distant. The idea that those points of light might have worlds orbiting them, worlds with their own skies and climates and geological histories, was something we could speculate about but never verify. Every philosophical tradition that engaged with the question came to different conclusions. Some held that Earth was unique, the center of existence, the only world that mattered. Others argued that an infinite universe must contain infinite worlds. Neither position was based on evidence. Neither could be, because until very recently in the long arc of science, we had no tools capable of detecting something as small and dark as a planet around a star that might be hundreds of light years away. The fundamental problem is contrast. A planet orbiting a distant star is like trying to spot a moth circling a stadium floodlight from several miles away at night. In fog, the floodlight is billions of times brighter than the moth, and the distance means even the floodlight is barely visible. Stars are billions to trillions of times brighter than any planet orbiting them. At the distances we're talking about, any reflected light from a planet is completely drowned in the stellar glare. Early telescopes had no hope of resolving the two signals from each other. The question remained open and technically unanswerable for centuries. Philosophers speculated. Astronomers measured star positions and spectral compositions. Nobody could peer through the distance and the glare and say with certainty, yes, there is a world there. That changed in the early 1990s. In 1992, astronomers Alexander Wolszin and Dale Frail announced the discovery of two planets orbiting a pulsar, a rotating neutron star about 2,300 light-years away in the constellation Virgo. A pulsar is the collapsed remnant of a massive star that ended its life in a supernova explosion. It spins rapidly, emitting beams of radiation as it rotates like a cosmic lighthouse, and it pulses with such extraordinary precision that scientists can detect tiny wobbles in its timing caused by the gravitational pull of orbiting planets. These were the first confirmed exoplanets, and they were orbiting a dead star, a stellar corpse bathed continuously in intense radiation from the pulsar's relentless spinning. It wasn't exactly the hopeful beginning people had imagined for the search for other worlds. Then, in 1995, came the announcement that genuinely changed everything. Astronomers Michel Mayor and Didier Queloz discovered a planet orbiting a sun-like star called 51 Pegasi, about 50 light-years away. The planet, later named Dimidium, was roughly half the mass of Jupiter. It was orbiting so close to its star that one complete orbit took just over 4 Earth days. For days, Earth takes 365. For a planet that size to orbit that fast, it had to be nearly skimming the stellar surface. The temperatures on such a world would be catastrophic. But more than the temperature, what stunned astronomers was the orbit itself. Giant gas planets weren't supposed to exist that close to their stars. Every model of planet formation said they couldn't. Jupiter-sized planets needed to form far out in the cold outer regions of a protoplanetary disk, where the building blocks of gas giants can condense at low temperatures. The disk in the inner zone of a young star system is too hot for volatiles to condense, too hot for ice to form, too thin in solid material to build the cores that later accumulate gas envelopes. This planet had either formed in the outer system and migrated inward through some mechanism no one had fully modeled, or planet formation was far stranger and more varied than the scientific consensus believed. That discovery cracked open the entire edifice of assumptions astronomers had constructed around our own solar system as a template. Whatever rules applied to planetary formation apparently did not apply universally. Our solar system, it turned out, was not a representative sample. It was one outcome, one configuration among an enormous range of possible configurations. Mayer and Culo received the Nobel Prize in Physics in 2019 for that discovery. Since then, the confirmed exoplanet count has grown from 1 to more than 6,300. Missions like Kepler, launched in 2009, stared at over 150,000 stars simultaneously for 4 years, watching for the tiny, precise dip in brightness that occurs when a planet crosses in front of its host star from our line of sight. That transit method proved extraordinarily productive. TESS, the Transiting Exoplanet Survey satellite, launched in 2018, extended the search to cover almost the entire sky. Ground-based telescopes using the radial velocity method, which detects the slight wobble a planet's gravity induces in its star's motion toward and away from us, added thousands more confirmed worlds. And the picture that emerged from this expanding catalog was not what most people expected. The universe makes planets everywhere, every conceivable type, under conditions that stretch the word planet toward its breaking point. What follows is a tour of some of the most extreme among them. HD 189733b sits about 63 light-years away from Earth in the constellation Vulpecula. At first description, it fits a familiar category: hot Jupiter, gas giant in a close orbit, dayside temperatures around 1,832 degrees Fahrenheit, 1,000 degrees Celsius. The hot Jupiter class was the first type of exoplanet widely discovered, and it's well populated in the catalog. But HD 189733b is not merely another entry in that class. What makes it stand apart begins with its wind speeds. The planet has sustained atmospheric winds of approximately 5,400 miles per hour. The fastest wind gust ever recorded on Earth reached 253 miles per hour during Tropical Cyclone Olivia in 1996. The winds on HD 189733b are more than 20 times faster than that. And they're not gusts, they're permanent. A continuous, planet-wide atmospheric circulation operating at those speeds without interruption. No land mass breaks the flow. No mountain range creates turbulence that dissipates energy. No ocean surface absorbs heat and moderates the circulation. The planet is a gas giant, so the wind moves through gas against gas, cycling in enormous loops driven by the temperature gradient between the permanently hot day side and the cooler night side. The thermal energy flowing from day to night manifests as wind, enormous, unbroken, relentless wind at 5,400 miles per hour. But the wind alone isn't what makes HD 189733b genuinely disturbing. Its atmosphere has silicate particles. Silicates are what most rock is made of: silicon dioxide, the material of sand, quartz, granite, and the bedrock beneath every continent on Earth. On HD 189733b, silicate particles condense in the upper atmosphere in much the same way water vapor condenses into droplets to form clouds on Earth. The silicates form clouds made of glass. And those glass clouds, swept by 5,400 miles per hour winds, produce precipitation. Silicate droplets fall from those clouds under gravity. But because the winds are moving so fast, precipitation on HD 189733b doesn't fall straight down. It moves mostly sideways. Glass particles and droplets, molten or sharp-edged depending on where they are in the atmospheric column, blasting horizontally across the planet at speeds that make the concept of weather as a hazard completely inadequate. The physics here are not exotic. Silicate condensation in hot, dense atmospheres is predictable from basic thermodynamics. At the right temperatures in the upper atmosphere, silicates reach their condensation point just as water does in Earth's atmosphere. The resulting particles are swept by whatever the ambient wind speed is. Here, the ambient wind speed is 5,400 miles per hour. The particles go where the wind goes, which is sideways at all times. Astronomers have been able to confirm the atmospheric composition of HD 189733b in remarkable detail using transmission spectroscopy. When the planet passes in front of its host star, a tiny fraction of starlight filters through the thin atmospheric edge of the planet. different molecules absorb different wavelengths of that filtered light. By analyzing which wavelengths are depleted or absent in the transmitted light, scientists can identify the chemical components of the atmosphere. For HD 189733b, this revealed methane, water vapor, carbon dioxide, and the silicate signatures in the upper cloud layer. The planet's color was also measured. HD 189733b is a vivid, deep blue, not because of oceans the way Earth's blue comes from liquid water reflecting and scattering sunlight, but because of how its atmospheric chemistry scatters incoming starlight at a planetary scale. Combined with the way those silicate cloud layers interact with the star's output, it's a beautiful color for a place with no beautiful implications. A deep blue world wrapped in glass clouds, swept by permanent winds of 5,400 miles per hour, with glass rain moving sideways at all times. The visual from space would be striking. From the surface or from anywhere within the atmosphere, it would be the last thing you ever processed. WASP-12b is being consumed. Not metaphorically, not in some distant future or geological sense. Right now, in real time, the star it orbits is pulling material off the planet and drawing it into a stream of gas that spirals back toward the stellar surface. The planet is being eaten. WASP-12b sits about 1,400 light-years from Earth. It orbits its host star at a distance of roughly 2,200,000 miles. Mercury, the innermost planet in our solar system, orbits the Sun at about 29 million miles at closest approach. WASP-12b sits more than 10 times closer to its star than Mercury does to ours. At that distance, the gravitational forces from the star are not simply heating the planet, they're distorting its geometry. WASP-12b is no longer spherical. The star's gravity pulls harder on the hemisphere facing it than on the hemisphere facing away. The difference in gravitational pull across the diameter of the planet is large enough to permanently deform it. The planet has been stretched into an egg shape. The near hemisphere bulges visibly toward the star. The far hemisphere trails behind. The technical term for the threshold the planet has crossed is Roche lobe overflow. Every orbiting body has what's called a Roche lobe, the region within which its own gravity dominates over tidal forces from the object it orbits. If a body is pulled inside its Roche lobe limit, material at the inner edge becomes gravitationally unbound from the planet. The parent star can then capture that material. WASP-12b is past this limit. The star is actively stripping mass from the planet's upper atmosphere. Scientists estimate the mass loss rate at around 6 billion tons per second, every second. That is an enormous number in absolute terms. But the planet is a gas giant with a mass roughly 1.5 times Jupiter's. With that reservoir to draw from, the planet still has an estimated 3 million years before the star finishes consuming it. 3 million years sounds long, but in the context of a star system that has been around for billions of years, it is a brief final chapter. WASP-12b is also one of the darkest natural objects known in the galaxy. Its albedo, the fraction of incoming light it reflects back into space, is below 0.06. Earth reflects about 30% of incident sunlight. The Moon reflects about 12%. Charcoal reflects around 4%. WASP-12b reflects less than 6% of the light that hits it. The dayside temperature has been measured at roughly 3,992 degrees Fahrenheit, 2,200 degrees Celsius, hot enough to vaporize most metals. Iron's boiling point is around 5,072 degrees Fahrenheit, 2,800 degrees Celsius. WASP-12b sits below that, but well within the range where metals exist as vapor in the atmospheric chemistry. The night side, significantly cooler, is still far above any temperature that would permit liquid water or organized chemistry of any useful kind. The overall picture of WASP-12b is of a planet in the terminal phase of its existence. A gas giant that formed billions of years ago somewhere in the outer reaches of its system, migrated inward over geological time, and is now spending its final tens of millions of years being slowly absorbed by the thing that has been cooking it from the beginning. The star will not notice when it's done. It will simply be a star with slightly more mass than before. The planet will simply no longer exist. Gliese 436b is about 30 light-years from Earth, orbiting a small red dwarf star in the constellation Leo. It's roughly the size of Neptune, and it has water, not oceans, not ice caps, not water vapor in the atmosphere, something far stranger. The surface temperature of Gliese 436b is approximately 572 degrees Fahrenheit, 300 degrees Celsius. Water boils at 212 degrees Fahrenheit, 100 degrees Celsius at Earth's standard atmospheric pressure. So there is no liquid water on Gliese 436b, and given the temperature, there should be no ice either. But Gliese 436b is massive for its size, much denser than it looks. The mass generates gravity, and gravity generates pressure. Deep inside Gliese 436b, the water layers are under pressure so extreme that they physically cannot transition into steam, regardless of temperature. The pressure prevents the water molecules from expanding into a gas phase. They are locked in a compressed solid state not by cold but by force. This is Ice 7. Water has many solid phases depending on temperature and pressure, not just the ordinary ice that forms at 32 degrees Fahrenheit, 0 degrees Celsius. Ice 7 is one of the exotic high-pressure phases. It forms at pressures above about 30,000 atmospheres. Earth's entire atmospheric column at sea level exerts 1 atmosphere of pressure. Ice 7 requires 30,000 times that. Inside Gliese 436b, the gravitational compression of its mass creates those pressures and exceeds them in the deep interior. Water is forced into that compressed crystalline state at temperatures where, on Earth, it would be steam. This is hot ice. Solid water maintained in its solid phase not by temperature but by crushing gravitational force, at temperatures far above the normal boiling point. The planet has a mineral vapor atmosphere above the surface. Below that, a layer of superheated compressed water in an exotic solid phase. And deeper still, a rock and iron core under conditions that produce mineral structures not found anywhere in our solar system. Scientists who study Gliese 436b use the label warm Neptune, which technically describes its size and orbital temperature. What it doesn't capture is that the word water, when applied to this world, no longer carries any of its ordinary meaning. Water is the molecule, but none of the familiar phases of water, liquid, gas, ordinary ice exist here. Only the exotic high-pressure variant that nature produces only under crushing gravitational force. A world that has water without having water in any sense you would recognize. PSR B1257+12 is a pulsar about 2,300 light-years from Earth in the constellation Virgo. It spins about 161 times per second. 3 confirmed planets orbit it. The planets themselves are not the central disturbing fact about this system. The disturbing fact is where they came from. A pulsar is the remnant left after a massive star dies in a supernova. The supernova is not a gentle transition. The outer layers of the original star are expelled at a significant fraction of the speed of light. The core collapses in less than a second to a ball of neutrons about 12 miles across. The energy released in that collapse is staggering. In those brief moments, the energy output exceeds what the sun will produce across its entire 10 billion-year lifespan. A shock wave tears outward through the expanding stellar material. Any planets that existed around the original star before the supernova would have been obliterated outright or flung out of the system by the violence of the explosion and the sudden loss of most of the parent star's mass. The planets we detect around PSR B1257+12 almost certainly did not exist before the supernova. They formed afterward from the debris, from the shattered and scattered material thrown outward when the star's core collapsed. Over millions of years following the supernova, that debris disk redistributed itself around the newly formed neutron star. Clumps formed. Those clumps secreted more material. Eventually, they became planets born from a supernova, assembled from the remnants of a stellar catastrophe. And they exist in an environment defined by that catastrophe's ongoing remnant. Pulsar doesn't merely spin, it radiates. It emits enormous quantities of X-rays and gamma rays, along with the radio beams that define pulsars. The 3 planets in this system are permanently bathed in this radiation. There is no atmosphere thick enough, no magnetic field strong enough, no geological process capable of intercepting or deflecting what PSR B1257+12 sends in their direction every fraction of a second. These planets are perpetually irradiated at intensities that would destroy any molecular organization on contact. The surfaces of these worlds are continuously sterilized by high-energy radiation on timescales so short that any chemistry attempting to organize itself would be disrupted before it could proceed. They exist. They are real. They orbit a stellar corpse. They were born from the violence that created that corpse. And they will orbit their pulsar indefinitely, soaking in its radiation until physics eventually runs down the pulsar to silence, which will take an extraordinarily long time. These are the worlds where the confirmed exoplanet catalog began. An inauspicious start, and an honest preview of what the rest of the catalog would reveal. Coro 7b was the first rocky exoplanet to have its density measured precisely enough to confirm a rock and iron composition. It sits 480 light-years away in the constellation Monoceros, about 1.5 times Earth's radius, 5 to 6 times Earth's mass, density consistent with a silicate and iron interior. When that measurement was published, the scientific community registered something like excitement. The first confirmed rocky world outside our solar system. A planet built from the same basic ingredients as Earth, Venus, Mars, and Mercury, a terrestrial world. Then people looked at where it was orbiting. Coro 7b orbits its host star at about 1.6 million miles. The dayside temperature is estimated at between roughly 3,600 and 4,900 degrees Fahrenheit, 2,000 to 2,700 degrees Celsius. This temperature range isn't merely hostile to life. It's hostile to the rock itself. Silicon dioxide, the dominant component of most crustal rock on Earth, has a boiling point of around 4,172 degrees Fahrenheit, 2,300 degrees Celsius. On the dayside of Coro 7b, you are at or above the boiling point of rock. The surface isn't flowing as lava, which requires somewhat lower temperatures to remain liquid but solid at the surface level. The surface is vaporized. The rock transitions directly into a gas phase. The silicate minerals that constitute the crust exist not as solid ground or even molten lava, but as vapor in the atmosphere. And what happens when rock enters the atmosphere as vapor? The same thing that happens when water evaporates into Earth's atmosphere. It rises. It moves through the atmospheric column. It reaches cooler regions at higher altitudes or toward the terminator. It cools below its condensation point, condenses into droplets. It falls. On Earth, that cycle produces rain. On Coro 7b, that cycle produces rock rain. Silicon dioxide, magnesium oxide, iron vapor, calcium oxide, and other mineral compounds rise as gas from the superheated dayside. They move through the atmosphere. They cool as they drift toward the terminator and beyond. They condense into molten mineral droplets. Those droplets fall toward the surface, cooling further as they descend. By the time they reach lower altitudes, they may have solidified into hard particles. Rock falling from the sky. The first confirmed rocky world beyond our solar system is a world where it rains rock. The night side of Coro 7b sits at roughly minus 328 degrees Fahrenheit, minus 200 degrees Celsius. The temperature difference between dayside and night side exceeds 2,000 degrees, not varying with seasons, not cycling through moderate ranges as orbital distance changes. Permanent, fixed. One hemisphere where rock boils, the other locked in conditions cold enough to freeze carbon dioxide solid. A tidally locked world with the most extreme thermal gradient of any confirmed rocky planet. And between them, a thin terminator zone where mineral vapor cools enough to rain back down as molten drops onto whatever surface lies below. Kepler 78b has a profile that might initially seem almost familiar. Rocky, iron-bearing, about 20% larger than Earth, similar density to our planet. A rock and iron world. Then you check its orbit. Kepler 78b completes one revolution around its host star in approximately 8.5 hours, not 8.5 days. The planet sits about 700 light-years away. This host star is a Sun-like G-type star. For a planet to orbit that fast around that type of star, it has to be at a distance of less than 900,000 miles from the stellar surface. The resulting surface temperature is estimated between roughly 3,600 and 5,400 degrees Fahrenheit, 2,000 to 3,000 degrees Celsius. Every rock-forming mineral is molten. The entire planet is a lava world. Its surface layers are permanently liquid, constantly churned by tidal forces from its nearby star, and heated from within by the extraordinary tidal friction those forces generate. But what makes Kepler-78b genuinely puzzling is not its conditions, it's that it shouldn't be there. Planet formation theory is explicit on this point. The innermost region of a stellar system is cleared out early. Material that forms too close to the host star either falls inward under the pressure of the protoplanetary disk's inner edge dynamics, or gets blown outward by stellar radiation and stellar wind before it can accumulate into a significant body. There is no known pathway by which a rocky planet the size of Kepler-78b could have assembled at its current location. And it doesn't match the profile of any object that could have migrated there from farther out. The migration mechanisms that bring hot Jupiters inward through a disk work for giant planets. Small rocky worlds don't have the gravitational influence to execute those migrations. Kepler-78b is an anomaly, a lava world in an orbit it shouldn't occupy, with no consensus explanation for how it arrived there. And layered on top of that mystery is a second problem. At its orbital distance, tidal interactions with the star are not only heating the planet, they're decelerating it. The tidal bulge raised on the star by the planet's gravity slightly leads the planet's position. This creates a small gravitational torque that transfers angular momentum from the planet's orbit to the star's rotation. The planet loses orbital energy. As orbit shrinks, Kepler-78b is slowly spiraling inward. In roughly 3 billion years, it will fall into its star. We are observing this world in the brief window between its mysterious arrival in this orbit and its inevitable end, a puzzle that won't survive long enough to be fully solved. HD 209458b didn't just reveal a planet. It opened the primary method of study that now drives almost everything we know about the chemistry of exoplanet atmospheres. It sits about 160 light-years away in the constellation Pegasus. A hot Jupiter, roughly 2/3 of Jupiter's mass, tight orbit, hot. When astronomers confirmed in the late 1990s that it transited its host star, they realized they now had a planet whose atmospheric edge intercepted starlight during every orbital passage. That filtered starlight carries the chemical fingerprint of every molecule it passes through transmission spectroscopy. That technique is now the primary tool used to characterize exoplanet atmospheres everywhere in the catalog. The James Webb Space Telescope was built with this application as one of its core scientific purposes. Hubble used it. Dozens of ground-based instruments use it. Thousands of confirmed atmospheric detections trace back to the observational approach that HD 209458b made possible. But beyond the method, what the planet contributed was a direct observation of what happens to atmospheres in tight orbits over long timescales. Observations with Hubble revealed a massive plume of hydrogen streaming away from the planet on the side facing away from its star, a comet-like tail of escaping gas. Hydrogen molecules gaining energy from the star's extreme ultraviolet radiation, reaching escape velocity, and bleeding off the planet into space. At the rate observed, the planet was losing roughly 10,000 tons of hydrogen per second. This process is called photoevaporation. The star's extreme ultraviolet and X-ray output heats the uppermost atmospheric layers to temperatures where individual gas molecules gain enough thermal energy to escape the planet's gravity entirely. Once free, stellar radiation pressure pushes them further, sweeping them into the visible downstream tail. HD 209458b is a live demonstration of this process in action. And the process is thought responsible for a gap in the exoplanet catalog called the photoevaporation desert. There are many hot Jupiters in the catalog. There are many rocky super-Earths. But in the intermediate range, hot Neptunes, planets with moderate gas envelopes in tight orbits, the catalog is nearly empty. The hypothesis is that hot Neptunes form, but closing orbits around active stars eventually strip their gas envelopes away. What started as a hot Neptune becomes a super-Earth. The rocky core survives. The gas disappears over billions of years, 1 10,000-ton cloud per second. HD 209458b didn't just reveal a planet. It revealed a gas giant being slowly reduced, not by any sudden event, but by the persistent, patient attrition of its star's radiation. Trace 2b is about 750 light-years away, a hot Jupiter, and it reflects less than 1% of the light that hits it. Coal reflects between 4 and 5%. The darkest material ever engineered in a laboratory, a carbon nanotube array designed for maximum optical absorption, reflects about 0.045%. Trace 2b's reflectivity falls between coal and that laboratory extreme. Darker than coal, approaching the most absorptive material humans have ever constructed. But it's a natural planet. The cause involves atmospheric chemistry. The atmosphere contains sodium and potassium vapor, both of which absorb light strongly across broad visible wavelength ranges. The presence of vaporized titanium oxide in the upper atmosphere may contribute another layer of absorption. The combination creates an atmospheric environment that swallows incoming photons with extraordinary efficiency. Almost nothing bounces back. The planet doesn't shine by reflected starlight. It smolders. The absorbed energy heats the atmosphere, and the planet radiates thermally in the infrared from its own absorbed warmth. Not borrowed light from a star, just heat. A black planet emitting heat, moving through its orbit in an almost invisible state, detectable primarily by the tiny dip it causes when it transits across the face of its host star, and by the infrared glow that measurements can distinguish from the star's own infrared output. A dark, hot, silent world that drinks in light and gives back almost nothing visible. ROX's 42Bb is the largest planet ever discovered. And that single fact immediately raises a question that astronomers are still arguing about, because at its size, calling it a planet at all is genuinely contested. It sits about 440 light-years away in the constellation Ophiuchus, orbiting a young star in the Rho Ophiuchi star-forming region. Its mass is estimated at approximately 9 times the mass of Jupiter. Jupiter is itself 318 times the mass of Earth. So what we are talking about is an object with nearly 3,000 times the mass of Earth. That is not a planet in any intuitive sense of the word. That is something else. Brown dwarfs are sometimes called failed stars, objects massive enough to begin the gravitational collapse that leads to stellar ignition, but not massive enough to sustain hydrogen fusion. They glow from the heat of their own formation, slowly cooling over billions of years. ROX's 42Bb sits right at the lower boundary of that category. Whether it qualifies as a planet or a brown dwarf depends on which definition you apply. But here is what is not contested. It glows, not from reflected starlight, but from its own heat. Its surface temperature is estimated at around 3,632 degrees Fahrenheit, 2,000 degrees Celsius. And at that temperature, it radiates in the infrared with a light that belongs entirely to itself. If you could observe it from a safe distance, you would not see a dark sphere lit by a distant star. You would see something luminous, a world large enough and hot enough to shine on its own terms. What makes ROX's 42Bb genuinely disturbing, beyond its size, is where it sits 157 astronomical units from its host star. 1 astronomical unit is the distance from Earth to the Sun. ROX's 42Bb orbits at 157 times that distance. At that distance, the standard mechanisms of planet formation do not work. The protoplanetary disk around a young star thins dramatically in the outer reaches. There is simply not enough material that far out to accumulate into something this massive through the gradual process that built our own planets. ROX's 42Bb should not be where it is at the size it is. The leading explanations involve either a gravitational instability in the outer disk, where the disk collapses directly into a massive clump rather than building up gradually, or a formation process more similar to how binary stars form than how planets form, which again raises the question of what it actually is. The system is young, only a few million years old by astronomical estimates, which is why ROX's 42Bb still holds so much of its formation heat. Over billions of years, it will cool. The glow will slowly fade. But right now, in this early chapter of its existence, it is the largest known planetary object in the catalog, producing its own light, orbiting impossibly far from its star, sitting on the boundary between planet and something we don't have a clean word for. A world that does not need a sun to be seen. Kepler-16b made an image reel that had lived in science fiction for decades. 2 suns. 2 suns setting over a horizon is the visual shorthand storytellers have used for generations to signal immediately that you are somewhere genuinely alien. Kepler-16b is the first confirmed planet discovered to orbit both stars in a binary system, sweeping around the outside of the stellar pair in what's called a circumbinary orbit. It sits about 200 light-years away in the constellation Cygnus, roughly Saturn-sized. Its orbital period around both stars together is about 229 days. From the surface of Kepler-16b, you would see two suns. The orbital geometry determines how they move relative to each other and relative to the planet throughout the year. At some points in the orbit, both stars appear close together in the sky. At other points, they're on opposite sides, rising and setting at different times. There are moments when both are above the horizon simultaneously. During those periods, everything casts two shadows at once. Two distinct shadows extending from every object at slightly different angles, shifting relative to each other as the stars' angular positions in the sky change. A rock casts two shadows. A standing person would see two shadows extending from their feet at two different angles simultaneously. If the wind blew dust past them, each dust particle would cast two shadows on the ground. There would also be single sun periods, when one star has set, and periods of near darkness when both are below the horizon. The light is never constant in the way Earth's daylight is constant. The shadow geometry is never identical on two consecutive days. Kepler-16b's equilibrium temperature is estimated around -130 degrees Fahrenheit, -90 degrees Celsius, cold enough that any surface would be frozen. It's likely a gas giant with no solid surface to walk on anyway. But the orbital mechanics are real, confirmed, working exactly as described. And since Kepler-16b's discovery, astronomers have confirmed more than a dozen similar circumbinary planets. The universe makes two sun worlds with regularity. The images storytellers invented for their alien settings turned out to be a real and recurring feature of planetary astronomy. Kepler-70b and Kepler-70c were reported in 2011 as a story of planets that were swallowed by a star and survived. The word reported matters here, because this case comes with a significant asterisk that needs to be said up front. Their host, Kepler-70, is about 4,150 light-years away. It's what astronomers call a subdwarf star, a compact, hot stellar remnant that forms when a star sheds most of its outer hydrogen envelope. Before Kepler-70 became this, it was a red giant. Red giants expand to hundreds of times their original stellar radius as they age and exhaust their core hydrogen. When Kepler-70 entered its red giant phase, the expansion was enormous. The stellar surface swelled outward to a distance that, in our solar system, would have extended past the orbit of Earth. Any planets orbiting closer than that expanding surface would have been engulfed, swallowed by the giant's outer atmosphere. For a planet inside a stellar envelope, the conditions are extreme. The gas is millions of times less dense than the stellar surface, but still hot enough to strip planetary atmospheres rapidly. The drag from the surrounding stellar gas decelerates the orbital speed. The orbit decays inward. Some models suggest planets could spiral all the way into the stellar core before the giant phase ends. Others suggest the outer envelope expansion is slow enough, and the planet massive enough, that dense planetary cores can survive inside the red giant for millions of years as the outer layers slowly dissipate. What we see orbiting Kepler-70 today may be the surviving remnant cores of worlds that were inside a star, their outer layers stripped, their gas envelopes gone, only the compressed interiors remaining. Kepler-70b orbits at a distance smaller than the star's own radius. It orbits within a region that was, in the recent astronomical past, the interior of a stellar giant. The surface temperature of Kepler-70b is estimated around 12,632 degrees Fahrenheit, 7,000 degrees Celsius. The surface of our Sun is roughly 9,932 degrees Fahrenheit, 5,500 degrees Celsius. Kepler-70b, if it exists, is hotter than the surface of our own star. That conditional matters. The original detection relied on measuring faint reflected light rather than a transit. And subsequent analysis of the same data found that the signal can also be explained by pulsations within the star itself. Oscillations in its brightness that have nothing to do with orbiting planets. More recent work has leaned toward that second explanation, suggesting Kepler-70b and Kepler-70c probably don't exist at all. The scenario they were built to describe, a planet's dense core surviving inside a red giant and emerging naked and scorched, remains a real and studied possibility in planetary science. It just may not be what happened here. Worlds that may have gone through a star, or may never have been there to begin with. The Kepler-11 system doesn't present one disturbing world. It presents 6, packed into a configuration that challenges intuition about how many planets can coexist in the inner region of a single star. 6 confirmed planets orbit a Sun-like star about 2,000 light-years away in the constellation Cygnus. All 6 fit within an orbital region that, in our solar system, would sit inside the orbit of Venus. 6 planets between the star and a distance slightly less than Venus's orbital radius. The innermost completes an orbit in about 10 days. The outermost completes one in about 118 days. They are spaced so closely together in the gravitational landscape of their star that the system's stability depends on an extraordinary set of orbital resonances and gravitational interactions. When one planet passes another, the slight gravitational tug between them produces measurable changes in their orbital timing. These transit timing variations were used by astronomers to determine the masses of all 6 worlds. The results showed they are all low density. Even the largest ones, several times Earth's mass, have average densities far lower than Earth's. They have retained large fractions of hydrogen and helium gas, bloated, close-in worlds with thin but extensive gas envelopes wrapped around denser interiors. If you could stand on any surface they might have, which is uncertain for gas-dominated planets, you would see 5 other planets visible in the sky as disks, not points of light the way planets appear from Earth. Actual globes, some of them at angular sizes that would dwarf the full moon's apparent diameter as seen from Earth, moving visibly across the sky on their close, fast tracks. A sky dominated by neighboring worlds, each exerting a gravitational presence the others can measure. The system works, barely. It operates at the edge of its own stability. 6 planets negotiating their shared orbit through a constant, delicate gravitational conversation. HD 80606b's orbit is defined by extremity. Its eccentricity is approximately 0.93. Earth's eccentricity is 0.017, nearly circular. HD 80606b traces a dramatically elongated ellipse around its host star. At its farthest orbital point, it sits at a distance roughly comparable to Earth's from our Sun. At closest approach, it swoops to within about 3 million miles of the stellar surface. The ratio between farthest and closest distance is roughly 100 to 1. The temperature swing across one complete orbit is catastrophic in any meaningful sense of that word. In the cool distant phase, the planet's temperature is several hundred degrees Fahrenheit, a few hundred degrees Celsius, cool by hot Jupiter standards. As it plunges inward toward the star on the fast-narrowing ellipse, the temperature surges. Observations captured one of the most extreme heating events ever measured for any planetary body. The dayside temperature increased by more than 540 degrees Fahrenheit, roughly 300 degrees Celsius, in about 30 hours as the planet passed through periapsis. The atmospheric dynamics during that heating event were modeled from the thermal data. The conclusion was that the flash heating drives enormous atmospheric shock waves. As one hemisphere is suddenly exposed to the full intensity of the star at close range, the temperature differential across the planet's atmosphere drives supersonic winds, a thermal shock wave rolling across a Jovian-scale world. Then the planet swings back outward. The temperature drops over weeks. The atmosphere slowly returns to a cooler configuration. Eventually, the planet reaches its most distant point. A few weeks of relative cool. Then the plunge inward begins again. Flash heating, atmospheric shock, then slow cooling. Every single orbit. The system itself is a binary. A wide companion star orbits the primary at a considerable distance. This companion is thought responsible for the orbit's extreme eccentricity. Through the correlative mechanism, a distant stellar companion can pump up the eccentricity of an inner planet's orbit over millions of years through secular gravitational interactions. HD 80606b's orbit may once have been nearly circular. The companion star warped it across geological timescales into the comet-like trajectory we observe today. A planet whose entire year is defined by a sprint toward fire and a long retreat into the cold. GJ 1214b is about 40 light-years away in the constellation Ophiuchus, about 6 times Earth's mass, about 2.5 times Earth's radius. The category it occupies, mini-Neptune or sub-Neptune, places it between Earth-like rocky worlds and fully gas-dominated planets. And its interior is likely dominated by water under conditions nothing in our solar system matches. The surface temperature is around 500 degrees Fahrenheit, 260 degrees Celsius, well above water's boiling point at standard pressure. But GJ1214b is massive enough that its gravity generates enormous interior pressure. Water in the deep interior cannot transition to steam regardless of temperature. The pressure locks it into a compressed solid phase, hot ice, solid water maintained not by cold, but by force. The James Webb Space Telescope targeted GJ1214b's atmosphere and found it thick and spectrally featureless in transmission. A flat spectrum where you'd expect molecular signatures if the atmosphere were a thin, clear hydrogen envelope. The most plausible explanation is a dense layer of high-altitude clouds or aerosols blocking the view of whatever lies beneath. The same way Venus's thick sulfuric acid cloud deck makes the surface invisible from space. We cannot see through the clouds of GJ1214b. The best models suggest a water-dominated interior surrounded by a high-pressure atmosphere, but the cloud layer prevents confirmation. The planet has its secrets. We can measure its size and mass. We can confirm it has an atmosphere. But everything below that cloud deck remains hidden from us behind a veil that our best current instruments cannot penetrate. A world that won't show us what it really is. The way astronomers talk about exoplanet atmospheres has changed dramatically in the last decade. In the early years of the field, simply detecting that an exoplanet had an atmosphere at all was the goal, and the instrument sensitivity required was barely within reach. The first atmospheric detections, finding sodium in the atmosphere of HD 209458b in 2001, were celebrated precisely because they were so difficult. 2 decades later, the James Webb Space Telescope produces spectral data detailed enough to identify specific molecular abundances and constrain atmospheric models. The field has moved from detection to characterization, from knowing an atmosphere exists to understanding what it's made of and how it behaves. And what that characterization is revealing across dozens of planets now observed in atmospheric detail is that the universe's planetary atmospheres are nothing like Earth's. They're hotter, more chemically exotic, often in chemical disequilibrium, meaning they contain molecules that shouldn't coexist at the observed temperatures if chemistry had reached a stable endpoint. The presence of chemical disequilibrium in a planetary atmosphere actually carries information. On Earth, the oxygen in our atmosphere is in chemical disequilibrium. At thermodynamic equilibrium, oxygen would react with other molecules and disappear from the atmosphere over geological timescales. The only reason oxygen persists in Earth's atmosphere is that life continuously replenishes it through photosynthesis. The disequilibrium is a biosignature. In other exoplanet atmospheres, chemical disequilibrium is present for purely abiotic reasons. Vertical mixing in the atmosphere can carry gases from deeper, hotter layers up to cooler levels where they're out of equilibrium with their surroundings. Photochemistry, the breaking of molecular bonds by stellar radiation, creates reactive species that wouldn't exist in a purely thermally controlled system. These processes produce signatures in atmospheric spectra that look, to an untrained eye, like they might mean something biological. They don't. They mean the atmosphere is being actively processed by physical and chemical forces that have nothing to do with life. One of the most important scientific challenges in exoplanet atmospheric characterization is learning to distinguish disequilibrium caused by atmospheric dynamics from disequilibrium caused by biology. This is the context in which the K2-18b dimethyl sulfide detection needs to be understood. Dimethyl sulfide on Earth is produced by life. But whether dimethyl sulfide can be produced by atmospheric chemistry or by the interaction of a high-pressure water interior with a hydrogen-rich atmosphere under the radiation environment of a planet's red dwarf has not been fully modeled. The answer is not obviously no. The molecule has to be confirmed first. Then the non-biological mechanisms have to be ruled out. Only then does the biological interpretation become the leading hypothesis. The science is moving in the right direction, but it's moving carefully because the history of exoplanet science is full of initial detections that later analyses revised or retracted. And because finding life elsewhere in the universe would be among the most significant scientific discoveries in human history, that significance demands extraordinary evidence. The question of what an exoplanet's interior looks like has been a persistent challenge for the field. We can measure a planet's mass from the gravitational wobble it induces in its star, and its radius from the starlight it blocks during a transit. From mass and radius, we calculate average density, a bulk property that hints at composition. A density similar to Earth's suggests rock and iron. A lower density suggests more light material, hydrogen, helium, or water. A higher density suggests a more compressed interior. But density alone doesn't tell you the internal structure. The same average density could result from very different layered configurations. A super-Earth with a large iron core and a thin rocky mantle would have a higher density than one with a smaller iron core and a thicker silicate mantle. Without additional information, you can't distinguish them. The additional information comes from tidal deformation measurements. How a planet's shape is distorted by its host star's gravity reveals something about how the interior responds to tidal forces. A rigid rocky interior resists deformation differently than a fluid or partially molten interior. These measurements are at the edge of current capability for most planets, but they're being pushed. For some close-in planets whose interiors are likely partially molten, tidal deformation signatures may be detectable in the precise timing of their transits. The interior structure of exoplanets, their layer boundaries, whether they have liquid cores generating magnetic fields, whether they have active volcanic processes, remains largely unknown. We're reading the surface of these worlds from their shadows, their wobbles, and their filtered starlight. The deeper structure is inference. The next generation of observations will push that inference further. But for now, the interiors of most exoplanets remain a kind of darkness within the darkness. One category of exoplanet that deserves discussion is what astronomers call ultra-hot Jupiters. Not just hot Jupiters, which have dayside temperatures in the range of roughly 1,800 to 3,600 degrees Fahrenheit, 1,000 to 2,000 degrees Celsius. Ultra-hot Jupiters, planets whose daysides exceed 3,632 degrees Fahrenheit, 2,000 degrees Celsius, and in some cases reach 7,232 degrees Fahrenheit, 4,000 degrees Celsius. KLT 9b, which sits at around 4,300 degrees, is the extreme case. But there are others. WASP 189b, about 300 light-years away, has a dayside temperature around 3,200 degrees. WASP 121b, about 850 light-years away, has a dayside around 2,500 degrees. These planets share a set of atmospheric characteristics that stem from their extreme temperatures. At temperatures above about 2,000 degrees, titanium oxide and vanadium oxide, which in cooler hot Jupiters produce a temperature inversion by absorbing radiation in the upper atmosphere, begin to break down thermally, and that inversion disappears. The atmospheric chemistry changes regime entirely. In ultra-hot Jupiters, the dominant absorbers in the upper atmosphere are atomic metals: neutral iron, ionized iron, neutral titanium, calcium ions, chromium. These have been detected directly using high-resolution ground-based spectrographs. The presence of atomic metals in the upper atmosphere is made possible by the extraordinary temperatures. On Earth, metals are solids. At a few hundred degrees, some metals melt. At a few thousand degrees, metals boil. In the upper atmosphere of an ultra-hot Jupiter, metals exist as gas. And when starlight passes through that metal-gas atmosphere, each metallic species leaves its unique absorption fingerprint. Iron absorbs at specific wavelengths, calcium at others, chromium at others still. High-resolution spectrographs on large ground-based telescopes can detect these individual signatures. They produce atmospheric spectra that look more like stellar spectra than planetary ones, because the chemistry is more like a stellar photosphere than a planetary atmosphere. Ultra-hot Jupiters are the most star-like planets we know of, atmospheres operating in stellar chemistry regimes on planetary surfaces, or on what we call surfaces of these gas giants, which are really just the layers where the atmospheric density becomes too high for incoming starlight to penetrate further. The detection of phosphine in the atmosphere of Venus in 2020 generated short-lived excitement and a long-running scientific debate that illustrates how careful atmospheric detections require us to be. On Earth, phosphine is produced primarily by biological processes and by industrial chemistry. In the absence of life or industry, phosphine is rapidly destroyed by photochemistry. The detection of phosphine in Venus's atmosphere at the reported level would have been difficult to explain without some exotic non-biological mechanism or some production process we hadn't modeled. The detection was made using the JCMT radio telescope in Hawaii and later reported with the ALMA radio telescope in Chile. It triggered immediate scrutiny. Teams around the world analyzed the data independently. The spectral feature that had been interpreted as phosphine turned out to be a contamination issue with some of the ALMA data. When reanalyzed, the phosphine signal dropped substantially, possibly below any detection threshold. The debate about whether any phosphine signal remains in the Venus data is still ongoing. But the episode illustrated something important about the state of atmospheric detection science. We are pushing instruments to their limits. The signals we're looking for are faint. The analysis pipelines that convert raw telescope data into atmospheric composition measurements involve many steps, each of which can introduce artifacts or uncertainties. When the signal is marginal, the interpretation can swing between detection and non-detection depending on how the calibration and analysis are done. This is not a failure of the science. It's science working as it should: careful claims, independent verification, revision when the evidence demands it. But it means that announcements of exciting atmospheric detections, whether for Venus or for K2-18b or for any other world, need to be held with appropriate uncertainty until they have been thoroughly and independently confirmed. The history of exoplanet science is full of detections that held up and some that didn't. The tools keep improving. The confirmations keep building. The catalog of what we actually know, confirmed to the standard the field demands, grows steadily but slowly, carefully, as it should. Upsilon Andromedae is a binary star system 44 light-years from Earth. It has at least 3 confirmed giant planets. The orbital architecture of its outer 2 planets disturbed astronomers when the orbits were mapped precisely. The 2 outer planets orbit in planes tilted about 30 degrees relative to each other. 30 degrees of mutual inclination between the orbital planes of 2 planets in the same system. Planets form from a rotating disk of gas and dust around a young star. All the planets that coalesce from that disk should end up orbiting in roughly the same plane. Natural variations exist and can be produced by planet-planet interactions during the formation phase. But 30 degrees of inclination between 2 planets' orbital planes is far beyond what normal formation and early system evolution produces. The leading explanation involves a gravitational scattering event. Early in the system's history, it probably contained an additional giant planet. A close encounter between 2 of those giant planets produced a gravitational slingshot. One planet was ejected, thrown into interstellar space at high velocity. A planet flung out of its system, departing on a hyperbolic trajectory, never to return. And the gravitational violence of that encounter reshaped the orbital planes of the surviving planets. The remaining outer 2 planets carry the geometric scars of that event. Their orbits are tilted by 30 degrees relative to each other. The system's architecture is a record of a body that no longer exists. The orbital geometry contains the memory of a planet that was thrown into the dark between stars billions of years ago. Its signature is in the mathematics of everything it left behind. Kepler 413b orbits a binary star system. Its orbital plane is tilted relative to the plane of the 2 stars' mutual orbit. And that tilt slowly precesses. It pivots over a cycle of approximately 11 years. As the orientation shifts, the planet's geometry relative to Earth changes. Sometimes Kepler 413b transits across its host stars as seen from here. Sometimes it doesn't. For stretches lasting roughly 840 days, the planet simply disappears from transit detection. Then the precession brings it back. The planet appears, vanishes, appears again on a multi-year cycle governed by the precession of its tilted orbit. More consequentially for anything on the surface, the planet's own axial tilt also precesses. Earth's axial tilt is about 23.5 degrees. It varies by only a few degrees over tens of thousands of years, kept in check by the gravitational stabilizing influence of our large moon. Kepler 413b has no moon of comparable scale. Its axial tilt can swing by dozens of degrees over just a few decades. The climatic implications are dramatic. Seasons on this world aren't driven by a fixed relationship between a planet's axis and a single star. They're driven by the interaction of a precessing axis with two stars that are themselves in mutual orbit, combined with the planet's own orbit around that binary pair. The climate doesn't follow a predictable seasonal pattern. It follows something closer to a random walk on decadal timescales. Decades of a climate dominated by one axial geometry, then a shift, then something completely different. A planet without any long-term climatic stability, without any predictable progression from one season to the next. What you'd experience on the surface, assuming it had one, is a climate that seems to have no rules. No trust that summer follows spring. No confidence that the cold years will end. Just unpredictable change on timescales of years to decades. K2-18b is 120 light-years away in the constellation Leo, about 2.5 times Earth's radius, about 8 times Earth's mass. It orbits in the habitable zone of its host red dwarf star. In 2023, astronomers analyzing James Webb Space Telescope data reported evidence of a molecule called dimethyl sulfide in the planet's atmosphere. On Earth, dimethyl sulfide is produced primarily by marine phytoplankton. It is a candidate biosignature, a chemical associated with biological processes. The announcement attracted considerable coverage. K2-18b was described in many news reports as a planet that might harbor life. The scientific picture is considerably more careful than those reports suggested. The dimethyl sulfide signal exists in the spectroscopic data, but it's at the edge of what James Webb can currently confirm with high confidence. It could be a genuine biosignature. It could be an instrumental artifact. It could result from non-biological chemistry under conditions not fully modeled for a planet with this kind of atmosphere and interior. That tentative detection didn't stay tentative for long. In April of 2025, the same team announced a second, stronger signal using a different instrument on James Webb, reporting concentrations thousands of times higher than anything found on Earth. The announcement reignited both the excitement and the skepticism. A team at the University of Chicago argued the signal could just as easily belong to ethane, an unremarkable gas with no connection to biology. In July of 2025, a NASA reanalysis confirmed the atmosphere is water-rich and complex, but found no conclusive evidence of dimethyl sulfide. The story is not a single announcement. It's a cycle: tentative detection, stronger claim, independent scrutiny, and a result that keeps landing on inconclusive. What K2-18b illustrates is the gap between what the data suggests and what we can actually conclude from 120 light-years away. The planet orbits a red dwarf. Red dwarfs are active stars. They produce stellar flares that carry ultraviolet and X-ray radiation capable of stripping atmospheric molecules and sterilizing surfaces. The habitable zone of a red dwarf is close to the star. Planets there are likely tidally locked, one hemisphere permanently facing the flaring star, the other permanently in darkness. The optimistic interpretation of K2-18b is alive and being taken seriously by researchers. So is every skeptical counterargument. What the planet represents right now is a world we cannot yet fully characterize. A world whose atmosphere contains a signal that might mean something extraordinary, or might have a mundane explanation that we haven't identified yet. And we are reading it from a thread of starlight that passes through a fraction of the planet's atmosphere a few hours every 33 days. That is all we have. That is the instrument. And the signal is right at the edge of what that instrument can confirm. The rogue planets deserve careful attention, because some of the most disturbing worlds in the galaxy don't orbit any star at all. A rogue planet is a planet-mass object that has been ejected from its host system through gravitational encounters, or that never formed in a stellar system at all. These objects drift through the galaxy with no parent star, no stellar warmth, and almost no stellar light reaching them. Their surfaces approach absolute zero over time as their internal heat slowly radiates away into space. We know they exist because of gravitational microlensing. When a massive object drifts between a distant background star and Earth, its gravity bends and amplifies the background starlight in a characteristic pattern that reveals the mass of the lensing object. Large microlensing surveys, including OGLE and the Korea Microlensing Telescope Network, have detected events consistent with free-floating planetary mass objects. Statistical analyses of the results suggest rogue planets may be more common than stars. If accurate, the Milky Way contains hundreds of billions of worlds without suns, drifting in the cold between stars. The conditions on such a world are disturbing in a quieter, emptier way than the glass storms of HD 189733b. There is no sun, no daylight cycle, no seasons, no external energy input of any kind beyond the extremely faint ambient radiation of the galaxy. The surface temperature depends entirely on how much heat remains from formation, leaking outward slowly. A rogue planet ejected relatively recently in astronomical terms might still be warm in the infrared. An object discovered in 2012 called CFSR 2149-0403 is a candidate for this category. Its temperature is around 261 to 621 degrees Fahrenheit, 127 to 327 degrees Celsius. Warm for an object with no star. But that warmth is the last echo of the gravitational compression and radioactive decay that heated it during formation. That heat radiates away slowly over billions of years. Eventually, the interior cools to the point where even the infrared glow fades, and then it's cold and dark, moving at whatever velocity its last gravitational encounter gave it. With no orbit to complete, no destination, no sun to return to, just motion through the cold space between stars, for as long as physics allows, which is, for practical purposes, forever. PSR J 1719-1438 b orbits a millisecond pulsar about 4,000 light-years from Earth in the constellation Serpens Cauda. The pulsar completes approximately 173 rotations per second. The planet completes one full orbit every 2 hours and 10 minutes. Its orbital distance is only a few 100,000 miles from the pulsar's surface. But the planet's composition is what matters most here. PSR J 1719-1438b has a mass roughly equal to Jupiter's. Its radius is only about 40% of Jupiter's. For a mass that large packed into a radius that's small, the implied density is approximately 23 grams per cubic centimeter. For comparison, a cubic centimeter of water has a mass of 1 gram. Iron has a density of about 7.8 grams per cubic centimeter. Earth's average density is about 5.5 grams per cubic centimeter. PSR J 1719-1438b is roughly 4 times denser than Earth. The only material that accounts for a planet mass object with that density is carbon in its most compressed crystalline form, diamond, or more precisely, a crystalline carbon lattice under extreme gravitational compression. Under the pressures generated by compressing a Jupiter mass object into 40% of Jupiter's radius, carbon doesn't form graphite or ordinary carbonate minerals. It crystallizes into the ultra-dense diamond structure lattice. The planet is thought to be essentially a sphere of compressed crystalline carbon. Its history traces back to what it used to be before the pulsar was a pulsar. The system likely contained an ordinary star and a binary companion star. Over billions of years, the companion transferred mass to the primary, spinning the primary up into a rapidly rotating millisecond pulsar. The companion, stripped of most of its mass, shrank. What remained was a remnant composed predominantly of carbon and oxygen. The gravitational compression of that remnant into a planet mass object produced the crystalline structure we infer today. 2 stars, billions of years of mass transfer. One star becoming a pulsar, the other becoming a diamond. A natural diamond at planetary scale, orbiting a neutron star spinning 173 times per second, bathed in radiation that would dissolve any organized chemistry instantly. The most beautiful material in geology at the most hostile location in the catalog. WASP 76b sits about 640 light-years away in the constellation Pisces. Tidally locked. Dayside temperature approximately 4,352 degrees Fahrenheit, 2,400 degrees Celsius. Night side around 1,500 degrees. Astronomers analyzing WASP 76b spectrum using the espresso spectrograph at the Very Large Telescope in Chile found something unexpected in the data. On the evening terminator of the planet, the boundary where the night side transitions to day, there was a strong signal of atomic iron in the atmosphere. Iron in vapor form. On the morning terminator, where day transitions back to night, that signal was significantly weaker. The asymmetry told a story. On the day side, temperatures of 2,400 degrees are well above iron's condensation point. Iron exists as vapor there, and the enormous thermal wind flowing from dayside to nightside carries that vapor across the terminator. When that wind reaches the night side, temperatures drop below iron's condensation point, and the vapor condenses into liquid droplets that fall. Iron rain falling on the night side of WASP 76b. As the iron rains out of the atmosphere on the night side, it is removed from the upper atmospheric layer. That's why the morning terminator shows less iron in the upper atmosphere than the evening terminator, where fresh vapor from the day side is just arriving. The iron has already rained out. WASP 76b cycles iron through its atmosphere the way Earth cycles water, evaporates on the hot side, carries across, condenses, falls. But the evaporation temperature is around 2,400 degrees, and the rain is iron. That interpretation is the leading one, but it isn't the only one on the table. Later analysis of the same data suggested the iron signal could also be explained by temperature differences across the planet rather than true condensation, and the question hasn't been fully settled. Either way, the day side is hot enough to vaporize metal, and something happens to that iron as it crosses into the dark. 55 Cancri E is about 40 light-years away in the constellation Cancer, 8 times Earth's mass, twice Earth's radius. Its orbital period is just over 17 hours, less than 1 Earth day per complete orbit. The orbital distance is approximately 2.5 million miles from its host star. The dayside temperature is estimated around 4,172 degrees Fahrenheit, 2,300 degrees Celsius, above the boiling point of most rock-forming silicate minerals. 55 Cancri E has been a priority target for the James Webb Space Telescope, partly because it's close enough to be characterized in detail, rocky enough to model compositionally, and hot enough that atmospheric signals might be measurable even at its resolution. Preliminary James Webb observations suggested the presence of an atmosphere. For a rocky planet this close to a sun-like star, maintaining an atmosphere is a significant challenge. At these temperatures and radiation levels, a lightweight hydrogen or water atmosphere would be stripped away rapidly. For something to persist in the atmosphere of 55 Cancri E, it needs to be composed of molecules heavy enough to survive the radiation pressure and thermal escape that would strip lighter gases. The data is consistent with an atmosphere of mineral vapors, silicon dioxide, sulfur dioxide, and related compounds that exist as solids on Earth but as gases at temperatures exceeding 2,000 degrees. A mineral vapor atmosphere above a surface that is, at minimum, partially molten. The boundary between the solid surface and the atmosphere is blurred on 55 Cancri E because the surface material and the atmospheric material are the same substance in different physical phases. Rock and rock gas, the same material at different temperatures at different altitudes. A world where the ground and the sky are made of the same thing. The exoplanet catalog has grown exponentially, but what it represents is still a small fraction of what exists. The Milky Way contains between 200 billion and 400 billion stars. Statistical analyses from the Kepler mission suggest nearly all of them have planets. If that's accurate, the galaxy contains hundreds of billions to trillions of planets. The more than 6,300 confirmed exoplanets represent a tiny fraction of that total. And what we've confirmed is not a random or representative sample. It's a biased sample. The transit method preferentially detects planets in tight orbits, since those transit more frequently and are easier to catch edge on. The radial velocity method preferentially detects massive planets close to their stars, since those produce the largest measurable wobbles. Both methods undersample planets analogous to the outer solar system, wide-orbit worlds in habitable zones, cool giants like Jupiter and Saturn, small rocky planets on multi-year orbits. These exist and have been confirmed, but in numbers that dramatically underrepresent their true frequency in the galaxy. Which means the catalog of disturbing worlds we've built tonight, extreme as it is, represents the most detectable fraction of the full planetary population. The quieter, cooler, more potentially habitable worlds are out there. We just haven't found most of them yet. And in the worlds we have found, the extremity we observe is partly a function of how the detecting methods work. We find the closest, hottest, most distorted, most extreme planets first. The full range of what the universe builds extends in both directions from those extremes, into the familiar, and into things we haven't yet imagined. There is also the matter of what astronomers call the cosmic shoreline, a concept developed by astrophysicist David Grinspoon and later formalized with Jonathan Lunine and others. The idea is that when you plot the escape velocity of a planet against the radiation environment it receives from its star, planets above a certain line on that plot retain their atmospheres. Planets below it don't. The line separates worlds with atmospheres from worlds without. Earth sits comfortably above the line. Mars sits uncomfortably below it. Venus, surprisingly, sits well above it, which is why Venus has an atmosphere despite receiving more stellar radiation than Earth. Venus's atmosphere didn't escape. It just transformed into something terrifying. Most close-in exoplanets sit in extreme positions on this plot, receiving vast amounts of radiation. Some have escape velocities high enough to hold onto their gas envelopes anyway. Others are caught in the slow attrition of photoevaporation. The cosmic shoreline is a reminder that atmosphere retention is not guaranteed. Earth retained its atmosphere because it has the right mass and receives the right amount of radiation. Change either variable significantly, and the outcome changes. Most of the worlds in tonight's catalog received a very different combination. What the catalog forces us to confront, taking all of these worlds together, is that the conditions on Earth are not the default state of a planet. They're not the average. They're a specific, narrow outcome of a specific set of conditions that came together in one place. Our planet orbits in the habitable zone of a stable G-type star, with the right atmospheric composition to maintain liquid water at the surface. Internal heating from radioactive decay drives plate tectonics, which cycles carbon through the system and stabilizes the climate over geological time. A large moon stabilizes the axial tilt, the same stabilizing influence Kepler 413b lacks, which is why its climate is chaotic. A strong magnetic field generated by Earth's liquid iron core deflects the stellar wind that would otherwise strip the atmosphere over billions of years. And Jupiter sits in the outer solar system, massive enough to have perturbed the comets and asteroids that might otherwise have bombarded Earth far more frequently. Every one of these conditions matters. Every one of them had to be right simultaneously, and every one of the worlds in tonight's catalog missed one or more of those conditions, sometimes by a dramatic margin, sometimes by a factor of thousands. The glass storms on HD 189733b result from a stellar proximity that makes the dayside too hot and the resulting wind speeds too fast for any chemistry to organize. The rock rain on Corot 7b results from a temperature so extreme that the surface material itself is in a gas phase. The hot ice of Gliese 436b results from pressure so extreme that water cannot be water in any recognizable form. The pulsar planets formed from a supernova and exist in the radiation field of its remnant. The diamond world orbits a neutron star. The rogue planets drift alone in the cold. These are what the universe builds, not by intent, not by preference, but because physics produces planets in all configurations that don't violate it. And most of those configurations are not the one that produces a stable, temperate, wet, chemically rich, magnetically shielded world that persists for 4.5 billion years. There are several more worlds in the catalog that haven't been covered yet. Each of them adds something to the picture. HAT P7b is a gas giant about 1,040 light-years away in the constellation Cygnus. Tidally locked. Dayside temperature around 4,892 degrees Fahrenheit, 2,700 degrees Celsius. When astronomers used data from the Kepler Space Telescope to map the temperature distribution across the entire planet, they found something unexpected in the thermal pattern. The brightest, hottest region on the planet wasn't on the exact substellar point, the point on the surface that faces directly toward the star. It was offset, shifted away from the center. The shift meant that the hottest part of the planet's dayside was being moved by atmospheric dynamics. Something was transporting heat from where the star deposited it to somewhere else. The wind pattern was shifting the peak temperature. Further analysis suggested that the wind patterns on HAT P7b aren't stable. They shift direction over time. The winds reverse, and as they do, the hottest region on the dayside moves. Sometimes it's east of the substellar point, sometimes west. The shifts happen on timescales of days to weeks. This kind of wind reversal was not something the models predicted for hot Jupiters. The expectation was a stable, predictable circulation from day side to night side. HAT P7b's atmosphere doesn't cooperate with that expectation. Its winds are variable. Its temperature pattern shifts. It's a planet where the weather is genuinely unpredictable, in the sense that the dominant atmospheric circulation reverses direction without warning. What drives this variability isn't fully resolved. The leading candidates involve magnetic interactions between the ionized atmosphere and the planet's magnetic field, or instabilities in the atmospheric flow that develop on certain timescales. Either way, HAT P7b adds something the catalog didn't anticipate: a hot Jupiter with weather that changes. Not in the sense of a light shower versus a thunderstorm, but in the sense that the entire planetary circulation pattern rotates between two different configurations. WASP-17b is about 1,000 light-years away in the constellation Scorpius. It's a gas giant, and it orbits its star in the wrong direction. Every planet in our solar system orbits the Sun in the same direction. Prograde, the same direction the Sun rotates, the same direction the original protoplanetary disk was spinning when the planets formed. The planets all formed from that disk. They all inherited its rotational direction. WASP-17b orbits its host star in the opposite direction from the star's own rotation. Retrograde. This is called a retrograde orbit, and it's deeply puzzling. A planet cannot form in a retrograde orbit around a star. The disk from which it would form is spinning in the prograde direction. A planet that forms from that disk orbits in the prograde direction. For a planet to end up in a retrograde orbit, something must have changed after it formed. The leading mechanism is, again, a gravitational scattering event. In a system with multiple giant planets, or with a wide stellar companion, gravitational interactions can flip a planet's orbital inclination over time. The correlative mechanism, which we discussed in the context of HD 80606b's eccentricity, can also drive inclination changes. If the inclination is driven high enough that the orbit crosses from a prograde tilt to a retrograde one, the planet ends up going backward. WASP-17b may have been scattered into an orbit tilted more than 90 degrees from the disk plane, at which point the planet is effectively in retrograde. The existence of WASP-17b demonstrates that planetary orbits can be dramatically reshaped by gravitational dynamics after formation. A planet that formed going one way can end up going the other way. The direction of orbit is not guaranteed. It is the outcome of whatever gravitational history the planet survived. Kepler-7b is a gas giant about 1,000 light-years away in the constellation Lyra. It was one of the first exoplanets to have its cloud structure mapped. The planet is tidally locked. What astronomers found when they assembled a temperature and reflectivity map of the planet from Kepler's photometric data was that the brightest region on the planet, the region with the highest reflectivity, was not on the day side directly below the star. It was shifted west, toward the evening terminator. This implied that the clouds producing the high reflectivity were not symmetric. They were concentrated on one side of the planet's day hemisphere. This was the first direct evidence of uneven cloud coverage on an exoplanet, with clouds preferentially forming on one side rather than distributing uniformly. The cause is the atmospheric circulation. On tidally locked planets, the day-to-night wind pattern doesn't simply flow straight across. The Coriolis effect, the same force that causes Earth's weather systems to rotate, deflects the airflow on a tidally locked planet. This deflection can produce a persistent asymmetry in cloud coverage. The clouds on Kepler-7b are thought to be silicate clouds, the same type found on HD 189733b, condensed mineral particles in the upper atmosphere, concentrated on the western part of the day side by the Coriolis-affected wind pattern. What Kepler-7b contributed to the catalog is a direct picture of cloud asymmetry, a planet where one side of the day hemisphere is brighter and more reflective than the other. Not because it receives more starlight, but because the wind pattern stacks the clouds there. Weather in a structural sense. Predictable, stable, geometrically defined weather driven by the rotation dynamics of a world with one permanent face toward its star. GJ436b and GJ3470b are two warm Neptunes that have been observed to be losing their atmospheres through a different mechanism than the hot Jupiter photoevaporation described earlier. These planets orbit red dwarf stars. Red dwarfs are less luminous than sun-like stars, but they compensate with higher extreme ultraviolet and X-ray output relative to their visible light output, and they're active for much longer. Sun-like stars calm down magnetically after a few 100 million years. Red dwarfs can remain magnetically active for billions of years. The sustained high-energy radiation slowly erodes planetary atmospheres over those timescales. For GJ 436b, observations using ultraviolet wavelengths from the Hubble Space Telescope revealed a giant cloud of hydrogen surrounding the planet, a comet-like tail of escaping atmospheric material streaming away from the planet. The tail is enormous relative to the planet itself. Its cross-section, visible in ultraviolet, is dozens of times the physical size of the planet. A giant atmospheric comet created by the radiation stripping of a Neptune-sized world. GJ 3470b showed a similar structure when observed. Both planets are thought to be in the process of losing their atmospheres entirely. Over the next several billion years, the sustained radiation from their red dwarf hosts will strip the gas envelopes down to whatever dense cores lie within. Two more examples of the photoevaporation desert being actively populated, warm Neptunes entering the process that will eventually turn them into bare rocky worlds, or leave whatever remnant their interiors contain exposed to space. The planet known as Kepler 452b attracted attention in 2015 when it was described as Earth's older cousin. It sits about 1,400 light-years away in the constellation Cygnus. It's about 60% larger than Earth in radius. It orbits a star similar to our Sun. Its orbital period is about 385 days, slightly longer than Earth's year. The orbital distance places it in the habitable zone. The host star is about 1.5 billion years older than our Sun. At the time of the announcement, this combination of properties generated considerable excitement. An Earth-sized planet in the habitable zone of a Sun-like star older than Earth, the implication that if life can arise, it's had even more time to do so here. The reality is more constrained. Kepler 452b is significantly larger than Earth, at 1.6 times Earth's radius. Models of its interior suggest it could be a rocky super-Earth, but it could also be a mini-Neptune with a significant gas envelope. The mass isn't directly measured. Without a mass measurement, the composition is uncertain. If it's rocky with a similar density to Earth, the surface gravity would be roughly twice Earth's. If it has a gas envelope, the surface, if any, would be under a thick, crushing atmosphere. The host star is also aging. As a Sun-like star gets older, its luminosity gradually increases. Our Sun is doing this too. In 1 billion to 2 billion years, the Sun will be bright enough to boil Earth's oceans. Kepler 452 star is already brighter than our Sun by about 10%, and its luminosity has been climbing over its longer life. Kepler 452b may be at the inner edge of its habitable zone, or past it. It may be undergoing the same runaway greenhouse effect that transformed Venus from a potentially temperate world into the sulfuric acid nightmare it is today. The older cousin label was appealing. The underlying astrophysics is more complicated. Kepler 452b is a genuinely interesting planet that highlights how careful we have to be about what the word habitable zone actually means. It means the temperature could allow liquid water. It says nothing about the atmosphere, nothing about the composition, nothing about the stellar activity, nothing about a dozen other factors that matter just as much. KLT-9b is the hottest exoplanet ever confirmed. It sits about 650 light-years away in the constellation Cygnus. Its host star, KELT-9, is one of the hottest stars with a known transiting planet, a blue-white A-type star nearly twice the Sun's mass, with a surface temperature of around 18,032 degrees Fahrenheit, 10,000 degrees Celsius. KLT-9b orbits this star at roughly 3.5 million miles. The dayside temperature of KELT-9b has been measured at approximately 7,772 degrees Fahrenheit, 4,300 degrees Celsius. For comparison, the surface of our Sun is about 9,932 degrees Fahrenheit, 5,500 degrees Celsius. KLT-9b's dayside is hotter than the surface of many stars. At those temperatures, the atmosphere of KLT-9b isn't composed of molecular gases the way most planetary atmospheres are. The heat is so extreme that molecules are torn apart. Molecular hydrogen, H2, dissociates into individual hydrogen atoms on the dayside. The bonds holding the molecule together are broken by thermal energy alone. At night, as the atmospheric flow carries the hydrogen to the slightly cooler night side, the atoms recombine into hydrogen molecules, releasing energy as they do. That released energy heats the night side. The cycle of dissociation on the day side and recombination on the night side is itself a form of energy transport, carrying thermal energy across the planet in the form of dissociated hydrogen. Metal atoms have been detected in KELT-9b's atmosphere: calcium, iron, titanium, magnesium, sodium, and several others, not as compounds, as individual neutral or ionized atoms. The temperatures are too high for these elements to bond with each other into stable molecules. They exist as a plasma-like gas of individual metal atoms suspended in a hydrogen atmosphere. KELT-9b is not just a hot planet. It's a planet whose atmosphere is being continually ripped apart by its own temperature. Molecules broken down to atoms. Atoms stripped of electrons in the upper layers. The entire atmospheric chemistry operating in a regime that exists nowhere else in our solar system, not even in the sun's outer layers, which are composed of similar materials but at somewhat different temperatures and pressures. KELT-9b's host star is also expected to evolve quickly. A-type stars burn through their hydrogen fuel faster than sun-like stars. KELT-9 is probably halfway through its main sequence lifetime already. When it exhausts its core hydrogen and expands into a subgiant and eventually a giant, KELT-9b will likely be engulfed. A planet already hotter than most stellar surfaces, orbiting a star that will expand to consume it within a relatively short astronomical time frame. Kepler-88b and Kepler-88c are two planets in the same system that interact gravitationally so strongly that their orbits can be used to measure their masses with precision. But the reason Kepler-88 is disturbing isn't about either of those confirmed planets. It's about what a third body in the system appears to be doing to both of them. Later observations suggested the presence of a third, much more massive object orbiting farther out in the system. If the mass estimates are correct, this outer body is a giant planet many times the mass of Jupiter, and its gravitational influence on the inner two planets is enormous. It drives large variations in the orbital periods of Kepler-88b and Kepler-88c through gravitational resonances. The inner planets' orbits are being continuously perturbed by the outer giant. Their orbital periods shift measurably from orbit to orbit. Their eccentricities are being pumped up and driven down by the gravitational interaction. From the perspective of anything on either inner planet, the solar system's architecture would be constantly changing in subtle but real ways. The length of the year would vary slightly from year to year. The distance from the star at closest approach would change over cycles driven by the outer giant's influence. Seasons, if they existed, would not follow a regular cycle. They would be governed not just by the planet's orbital mechanics relative to the star, but by the gravitational interference of a massive outer companion whose influence permeates the entire inner system. Kepler-88 is a reminder that planetary systems are not static. They are dynamical systems, constantly evolving under the mutual gravitational influence of every body they contain. Stability is not a given. It's an ongoing negotiation. HD 3167 is a system about 150 light-years away in the constellation Pisces that contains something highly unusual. Two confirmed planets whose orbital planes are tilted nearly perpendicular to each other. HD 3167b is a super-Earth orbiting very close to the host star, completing an orbit in less than a day. HD 3167c is a sub-Neptune farther out, with an orbital period of about 29 days. When astronomers measured the orientations of both orbits, they found the two planes were tilted by nearly 90 degrees relative to each other. One planet orbits roughly in the equatorial plane of the star. The other orbits nearly perpendicular to that. Two planets in the same system orbiting in planes nearly at right angles. This configuration is called a mutually inclined system, and it raises immediate questions about how the system evolved. Planets forming from a flat disk should all orbit in the same plane. A mutual inclination of nearly 90 degrees cannot develop during normal formation. Something dramatic happened after the system formed. The leading explanation involves a gravitational scattering event similar to what rearranged Upsilon Andromedae. An additional body, now absent from the system, produced the extreme orbital rearrangement before being ejected or destroyed. What remains is two planets going in dramatically different directions around the same star. Their orbital planes cross at the crossing points. If the timing ever aligned such that both planets were simultaneously near those intersection points, a close encounter would be possible. The current orbits may or may not be stable over geological timescales. The system may be in a state of ongoing slow evolution towards some different configuration, or it may have settled into a metastable arrangement that persists. Either way, HD 3167 is a system whose history was violent and whose present architecture reflects that violence in the misaligned orbits of two surviving worlds. The planet known as TOI 700d is about 100 light-years away in the constellation Dorado. It's roughly Earth-sized. It orbits in the habitable zone of its red dwarf host star, and it's one of the candidates that ongoing observation with the James Webb Space Telescope is targeting for atmospheric characterization. TOI 700d is tidally locked, one hemisphere permanently facing the red dwarf, the other permanently in darkness. Whether it has an atmosphere at all, and if so, what that atmosphere is made of, determines whether the planet is an interesting geological object or something potentially more significant. The James Webb observations are ongoing. Preliminary data has not conclusively detected or ruled out a substantial atmosphere. The planet represents what the next generation of exoplanet science is trying to answer. Not just whether a planet is in the habitable zone, but what the planet is actually like. Does it have an atmosphere? So, what is it made of? How does the atmosphere respond to the red dwarf's flares? Is there water? Is there anything that might indicate chemistry of interest? These questions cannot be answered from the mass and radius measurements alone. They require the kind of detailed spectroscopic observation that James Webb was built to provide. TOI 700d is in that pipeline. The answers, when they come, will either add another world to the catalog of interesting candidates or demonstrate that even Earth-sized, habitable zone planets around stable stars can be stripped of the conditions that matter. The question is live. The observation is underway. The result is not yet in. Proxima Centauri b is the closest confirmed exoplanet to Earth. It orbits Proxima Centauri, the star nearest to our solar system, at a distance of only about 4 light-years. 4 light-years, the closest star beyond our Sun, and it has a confirmed planet. Proxima Centauri b orbits its star every 11.2 days. Its orbital distance is about 4.5 million miles. That's close, very close by the standards of a habitable zone. But Proxima Centauri is a red dwarf. The habitable zone of a red dwarf is much closer to the star than Earth's distance from our Sun. At 4.5 million miles, Proxima Centauri b receives a similar amount of stellar energy to what Earth receives from our Sun. That's the basis for calling it a habitable zone planet. But Proxima Centauri is not a gentle star. It's an active flare star. It produces stellar flares regularly, sometimes large ones. Each flare sends a pulse of extreme ultraviolet and X-ray radiation toward any planet in the inner system. Without a strong magnetic field, those pulses can erode a planetary atmosphere over time. Whether Proxima Centauri b has a magnetic field strong enough to deflect those flares is unknown. Whether it retained an atmosphere through billions of years of exposure to Proxima's activity is unknown. The planet is also almost certainly tidally locked. At 4.5 million miles from a red dwarf, the tidal forces are strong. One hemisphere permanently facing Proxima Centauri, one permanently facing away into the cold. If an atmosphere exists, it circulates between the two hemispheres. If the atmosphere is thick enough to transport heat, the temperature difference between day and night might be survivable. If it's thin or absent, the day side bakes and the night side freezes. Proxima Centauri b is in the most complex position of any planet in the catalog. It's the closest, it's potentially habitable, it's potentially lethal, and it's close enough that future telescope technology might actually be able to directly image it. Not soon. Not with anything that currently exists. But within the conceivable future of astronomy, the direct detection of an Earth-sized world around the nearest star, with the ability to analyze its reflected light and search for atmospheric signatures, is not science fiction. It's an engineering challenge that the next generation of extremely large telescopes is being designed to begin approaching. Proxima Centauri b is where the closest answer to whether we are alone might eventually come from, or where the closest demonstration that even the nearest habitable zone planet is barren might be found. The closest star to Earth has a planet. That planet might have everything or nothing. We don't know yet. The study of exoplanet interiors has also revealed something important about the relationship between planetary composition and the stars they orbit. Stars form from the same cloud of gas and dust that eventually produces their planetary systems, so the chemical composition of that cloud determines what elements are available to both. Stars richer in iron tend to produce planets richer in iron. Stars with higher carbon-to-oxygen ratios may produce planets with fundamentally different mineralogy than Earth. On Earth, oxygen abundance means silicon bonds primarily with oxygen, producing silicate minerals. Where carbon is more abundant relative to oxygen, silicon bonds preferentially with carbon instead, producing silicon carbide, a completely different material with completely different properties than silicate rock. A planet made primarily of silicon carbide minerals would have a geology, a chemistry, and a surface environment unlike anything in our solar system. The planet PSR J1719-1438b, the Diamond World, is an extreme example of what happens when carbon dominates. But even among non-extreme cases, the chemical composition of the host star is a fingerprint for what its planets are likely made of. The diversity of stellar compositions in the galaxy means the diversity of planetary compositions is even larger than the diversity of planetary architectures. The materials the universe uses to build worlds vary as much as the orbits and temperatures those worlds experience. There is a single question underneath all of this that scientific exploration is slowly, carefully working toward answering. Is Earth typical? The preliminary answer from what the exoplanet catalog has revealed is no. Earth is not typical. The specific combination of conditions that make Earth the way it is appears to be uncommon. This doesn't mean Earth-like worlds don't exist. It means they're one configuration among many, and many of the other configurations look like the worlds described tonight. Whether any of those other configurations, or others we haven't yet discovered, can support life is a genuinely open question. Life on Earth is remarkably robust, existing in deep ocean vents with no sunlight in highly acidic environments in Antarctic ice in the upper atmosphere. It has demonstrated a capacity to exploit conditions that would have seemed impossible to biology a century ago. Whether life could exist on a world like Gliese 436b, or in the subsurface ocean of some rogue planet warmed by radioactive decay rather than any star, is not a question we can answer from here yet. What we can say is that the universe builds an enormous range of worlds. That range includes things nobody predicted: hot ice, diamond planets, iron rain, rock vapor atmospheres, worlds shaped like eggs, worlds with two shadows, worlds built from supernova debris, worlds drifting without any star. And the range almost certainly includes things we haven't found yet, configurations we haven't modeled, chemistry we haven't detected, conditions that don't fit any current category. The catalog is not finished. It's barely begun. This has been a long journey tonight through some of the most hostile, alien, and genuinely extreme worlds ever confirmed in our galaxy. A planet where glass falls sideways through 5,400 miles per hour winds. A world being eaten by its own star at 6 billion tons per second. A planet of hot ice, solid water maintained by crushing pressure at temperatures far above boiling. 3 planets born from the debris of a supernova. A world where rock vaporizes and rains back down as molten droplets. A planetary-scale diamond orbiting a neutron star. A world where iron condenses from the atmosphere on the night side and falls as metallic rain. Hundreds of billions of planets drifting with no sun, cooling slowly toward absolute cold. Every one of these worlds is real. Every detail in tonight's description comes from measurements, spectral data, transit timing signals, thermal emission maps, transmission spectroscopy, radial velocity measurements, microlensing events. The instruments we've built and pointed at the sky over the past 3 decades have returned all of this, not as speculation but as observation. The universe built these places. It builds places like these continuously in stellar systems everywhere, where the conditions tip one way or another toward the extreme. And it built one world around one average star on the outer edge of an ordinary spiral galaxy, where the conditions tip the other way, where rock is solid, where water is liquid, where the atmosphere is breathable and thick enough to be protective without being crushing, where a large moon holds the rotation axis stable, where a magnetic field wraps the whole planet in protection against stellar radiation, where the temperature ranges that exist here would be considered mild by the standards of almost every world in tonight's catalog. That is where you are, standing on it, breathing its air, sustained by every one of those conditions simultaneously, without thinking about any of them because they've always been there. The next time you look up at the stars, you already know what's probably orbiting most of them. You've seen the catalog. You know what the universe mostly builds. Glass storms, iron rain, lava oceans, worlds being consumed, worlds drifting in the dark. And then you can look back down at the ground you're standing on, solid, made of rock that is rock, not vapor, under a sky where clouds are water and the temperature is in a range that chemistry can use. This is the rare one, the weird outcome, the world that, against every tendency the universe, demonstrated in tonight's catalog, managed to be exactly this. Good night.